Today is about polygons, and this first couple of problems here, we are looking at some triangles, and some things that we note about triangles. First of all, how many degrees do we have inside of a triangle? 180, okay? And so on this first one here, not only do we know that it's a triangle, well, what kind of triangle do we have? It's equilateral, right? All three sides are marked the same. So if all three sides are marked the same, that also means that all three angles are also the same. And so we talked about that a little bit last semester. All three of those on the inside would have to be 60. Okay. The angle next to 60 here, this is what we call an exterior angle because it's on the outside, but these two angles together make a line. So if this one on the inside is 60, then the one right next to it would have to be what? It'd be 120, right? Because those two are supplementary and they form a line. So then we would say that x would have to be 120 degrees. Hey, this one here, we don't necessarily have to find this angle right here. We could say 180 minus these two, and that would give us our leftover angle here. And then we could do the 180 here. But the much easier way is these two interior angles added together equal x. So we could just go 64 plus 55 equals x. And that would be the easier way to go about it. But there's, as we've talked about before, there's a lot of different ways that we can approach certain problems. And that would give us 119. Okay. I know I said it a lot first semester, but always pay attention to what it is that is being asked, right? Sometimes it'll say solve for x. And I think on the final, those are some questions that were missed quite a bit. Because like sometimes we would solve for x, and then we would forget to plug it back in and find out what it is that we're trying to find or miss. And so those are questions that were missed, not necessarily because we did the math wrong, but because we didn't read the question carefully, and those kind of things. Okay, a couple of things, and I'm going to put this over here to the side. You guys have a little bit of room there to the side. The first thing that I'm going to talk about is types of polygons. You're going to see these names throughout this chapter, and some of these we already know, but some of them we maybe aren't quite as familiar with. So when we see these names, I want us to know what it means and what we're talking about. The lowest number of sides on a polygon would be 3. I can't have a two-sided polygon, but 3 would be our lowest. And we know that 3 is a triangle. And there's a lot of different kinds of triangles. We talked about equilateral and scalene and obtuse and acute and all those kind of things. But all we're talking about here is how many sides does it have? If it's 3 sides, it's a triangle. Okay, when I think of 4 sides, what's my first thought when I think 4 sides? When I say a 4-sided figure, what's something that pops in your mind? Square, yep. Square is a 4-sided figure. But we have just a generic name for any 4-sided figure. It doesn't have to have anything specific about it. Like a square has 4 right angles and 4 congruent sides. So a generic name that we use for a 4-sided figure is a quadrilateral. We're going to talk more and more about different types of quadrilaterals, like a square, a rectangle, a trapezoid, a rhombus, and things like that. But generic, we just call it a quadrilateral. 5 is a pentagon. There's actually a building in Washington, D.C. It's called the Pentagon because it has 5 sides to it. All 5 sides are 5 different wings of like government branches, like the CIA and things like that. Some of the military are housed in the Pentagon. It was actually one of the buildings that got hit in the 9/11 attacks, and it's been redone and all that. But Pentagon is a 5-sided figure. 6 is what we call a hexagon. 7 is a heptagon. 8 is an octagon. Some of these prefixes kind of make sense to us. Like a heptagon is not a prefix we see very often. Octagon, we see that like an octopus has 8 tentacles. Octagon has 8 sides. So the prefix oct means 8. 9 is one that we're going to see a little bit today, is a nonagon. It's not a real common one. And then 10 is a decagon. The prefix dec means 10, like a decade is 10 years. Decagon would be 10 sides. If we look at the number of degrees that would be on the inside, the interior of each one of these. Okay, so let's start with the triangle. Well, triangle we saw a lot first semester. How many degrees did we say were on the inside of a triangle? It was 180. Okay, always 180. Okay, a quadrilateral, like a 4-sided figure, like a square. A square has 4 right angles. So if I did 90 times 4, then that would make 360. And we're not going to memorize all these, okay? But I want you to kind of recognize a pattern that's going on here. Each time that we go down from one to the next, we're going to add 180 degrees. So we keep going up. As we add another side, we're going to add another 180. So then this would come up to be 540. And we could keep doing that as we go down, okay? But we wouldn't want to do that every single time. And so we have a formula that we actually use to help us figure this out. We're going to take the number of sides minus 2. So like on this one, for instance, we have 1, 2, 3, 4, 5 sides, right? We're going to take the number of sides in, which is 5, and we're going to do 5 minus 2 times 180. Okay, so like for a triangle, 3 minus 2 would be 1. 1 times 180 is still 180. Quadrilateral would be 4 minus 2 times 180. For a pentagon, 5 minus 2 is 3, and then 3 times 180 would be 540. Okay, so this little formula right here, n minus 2 times 180, is the formula we can use for any polygon. N is going to be the number of sides. That's what we're talking about here at the top of the next page. And there's your formula. Okay, that's going to be a really important formula for today. N is going to represent the number of sides that we have. Number of sides will change on each figure. We'll look at some today. I know I only went up to 10. We could obviously have more than that. That won't happen very often, but if I had like a 14-sided figure, I'm not going to ask you to draw a 14-sided figure very often, but if I had a 14-sided figure, then I could figure out how many degrees would be inside of that, and it would just be 14 minus 2 times 180. So you always got to decide how many we have, okay? And in this case right here, we don't know if all of these are equal or not. Probably not in most cases. Some are obtuse, some are acute. There's different measurements there, but we know that we can figure it out based off if we know the whole number. Okay, so we got to know that formula. That's a really big part of what we're doing. So on these first couple of problems, that's all we're doing. We're trying to figure out how many degrees are on the inside of the figure. And that's the key here, is that it's interior. Interior means on the inside. Okay? So we got to first of all figure out how many sides do we have. And just so you know, like where you start, because some of these are going to have a lot of sides to them. So sometimes I kind of like to mark it. And I'll go 1, 2, 3, 4, 5, 6, 7, 8. Sometimes we forget where we started counting at. That doesn't mean they're all equal. I'm just marking them to say I counted it already. Okay, so we have 8 sides here. So my formula would be 8 minus 2 times 180. Okay, and here's what I'm going to tell you. Using parentheses, if I'm going to put this into my calculator, using parentheses is going to be very, very crucial to what we're going to do. If you put this into your calculator without parentheses, what's your calculator going to do first? It's going to do the multiplication first. Your calculator is smart enough to say, I'm going to do the order of operations first. So that's why if I put it in parentheses, it's going to do the parentheses first, and then it's going to multiply. Or what you could do is just say, I don't really need to do 8 minus 2 in my calculator. Hopefully we can do 8 minus 2, right? And we can say 8 minus 2 is really 6. So then I can do 6 times 180. Hey, thank you. Appreciate it. And so then we're just doing 6 times 180, which is 1,080 degrees, okay? So the more sides that I have, the bigger the number is going to keep getting to be, okay? It just keeps adding more angles, more sides. And so the number is just going to continue to get larger and larger as I add more sides. Okay, an 11 gon, we don't have a special name for some of these, right? How often do we see an 11-sided figure? Not very often, okay? But this coin has 11 sides to it. It's a Canadian coin. And so if I wanted to figure out the angle, total angle measure here, 11 just tells me how many sides are in that coin, or on that coin. Okay? And I don't mind if you put this into the calculator like this, but you've got to make sure you put parentheses around it. Okay, that's why, just to avoid any problem, I would just go ahead and do the subtraction first, and then just do 9 times 180, and then you don't have to worry about making a mistake there. Okay, and so we get 1,620. Okay, just keeps going up, keeps getting bigger as we get more sides. Okay, on this one here, I'm going to show you a couple of different ways that you could approach this. It's kind of solving an equation. Once again, we know the formula to be n minus 2 times 180. But instead of them telling us how many sides we have, on this one, they tell us the total number of degrees. Okay? And some of these you're going to memorize, and you're going to say, okay, I know 900 is the same as this figure right here. Okay? Like we know 180 is a triangle. But some of them we don't. Okay? And so we got to be able to figure it out. So what we're going to do on this one is we're going to set the formula equal to 900. Okay, and there's two ways that you could solve this. I'm going to show you both ways, and you can kind of decide which way you like better. And I won't do both ways every single time. But if most of us saw this, what would be our first thought that we would have to do first? We probably would want to get rid of the parentheses, right? We would take 180. I heard somebody say, I heard somebody say it. What was? Divide by 180. Okay, so that's one way we could do it. We could divide by 180 right here. And so then I'm left with n minus 2. And then what's 900 divided by 180? 5. And then we would just have to add 2. I think that's the easier way to go. Okay? Is divide by 180 first and not distribute the 180 through. Okay? But a lot of times when we see a parenthesis right here, we think that we have to distribute that 180. And it's not wrong, okay? I could go 180 times n minus 180 times 2. Distribute the 180. And then we could add 360 to both sides. And then we would take 1260 divided by 180. And it still gives us n equals 7. Okay? You don't have to do both. But a couple different ways we can solve it. I probably prefer this one because the work's a little bit easier, a little bit cleaner. We don't have quite as big of numbers. So it's kind of up to you. If you're a distributive person and you like to distribute it and solve it the way you've always solved it, there's nothing wrong with that. Okay, so try this one down here. Use whichever method you want and solve for n. So if we did the dividing first, we divided by 180, 1440 divided by 180 would give you 8, and then you add 2 to both sides and you get 10. If you do the distributive, it would look a little bit different as you solve, but you should still get 10. Okay, if I don't get an answer here that's a whole number, that's a definite, what did I do wrong, right? We can't have like 7.5 sides or 9.5 sides on a polygon. That doesn't make sense. So your answer has to be a whole number on something like that. If not, you got to figure out where did I go wrong. Okay, we've seen a couple of these corollaries as we've gone throughout the year, and it's just kind of like some information that's attached on to the theorem that we just got done doing. Okay, and so the theorem that we just got done doing was talking about the inside angles of any polygon, and we talked about using n minus 2 times 180. But the sum of the measures of a quadrilateral. So a quadrilateral is one of those figures that we're going to see a lot over the next couple of weeks. We're going to see squares, rectangles, all of those. Those are all quadrilaterals. And so it kind of has its own special corollary because we're going to see it so much. And so when I see, kind of like when I see a triangle, I know that a triangle is always 180. When I see a four-sided figure of any kind, I need to always know that four-sided figure is always 360. So a quadrilateral is always 360 every time. Okay? You shouldn't have to figure it up. You should just know. If I see four sides, I know it's 360. If it's a square, if it's a rectangle, if it's any four-sided figure, it's always 360. So here, when I see both of these, I know both of these are equal to 360 because both of these are four-sided figures. They're different, completely different figures, right? But the total number of degrees on the inside are still going to be the same. So to solve here, we're going to add all of these together. And we're going to solve for x. Okay? And there's a couple different ways that you could approach this too. Okay? You could subtract each one of these one at a time from 360. It's okay. What I probably would rather do, I think it's a little bit quicker, is combine like terms over here on the left, put all three of those angles together, add up what they're going to be. So let's add 108 plus 121 plus 59. What does that add up to be? 288, okay. And then to get x by itself, we would just subtract 288, and then we're left with 72 degrees. Okay, this one here would be very similar. This one does not tell us the angle measure, but because we see the little square, what do we know immediately? It's 90, okay? Whenever we see that square marking, we always know that that is 90. And so what you could do right away here is you could just go ahead and add 74 plus 90 plus 141. Rather than writing it all out, you could just add those three angles all together. What would those three add up to be? 305. Okay. And then once again, we subtract 305 from 360, and we're left with 55 degrees. Okay. I will tell you with angles, it is possible to get an angle that's a half, okay? So I could, when I deal with angles, I might get a half an angle or half a measure of an angle. When I talk about number of sides, we can't do that, okay? When I talk about side length, I could get a half. So are we talking about an actual number of sides, or are we talking about length of sides? Are we talking about actual angle measure, or are we talking about how many angles we have? Okay, so that's a real big difference. Sometimes we think, oh, I can't get a decimal, and sometimes it is possible. And that kind of leads into this next question. Once again, we have a quadrilateral. I don't know any of the angles in the quadrilateral. Okay, we have 4 angles, all 4 of them are unknown. So we have x, 3x, 5x, and 7x. We're going to add all of those together. And set it equal to 360. Once again, the key word in this problem is that it's a quadrilateral. That tells me it's 4 sides. We know immediately that it is 360. Because these all have x attached to them, they're all like terms, right? So remember, if there's nothing in front of this x, there's an assumed 1 right here. So 1x plus 3x would be 4x. 4x plus 5x would be 9x. 9x plus 7x would be 16x equals 360. So then we got to solve for x. We got to get x by itself. So I take 360 and divide it by 16. What do we get? Okay. Is it okay to get half of an angle here? Half of a degree? Yeah, because we're talking about angle measure, okay? Angle measure will not always be exact. It's not always going to have to be a nice whole number. I can have half of a degree. And so in this case, x is 22.5. And when I say what are the 4 angles in this quadrilateral, the first one would be 22.5. And then I'm going to plug that back in. I'm going to take 22.5 times 3. 22.5 times 5. 22.5 times 7. And the way that you could check this then is add all 4 of these together, and it should add up to be 360. Now, do you have to do that? Not necessarily, but remember, that's always a good thing to go back, and if I'm not sure, if it doesn't seem right, and if it doesn't look right, does that make sense? And those should add up to be 360 if it all works together. Okay, these 3 terms are pretty important, and we've seen 2 of these before, okay? But the third one, we haven't seen as much. Maybe we just barely scratched the surface of it. Equilateral, we saw with triangles. Equilateral triangle meant all 3 sides of the triangle were the same. Now if I say I have an equilateral polygon of any kind, could be hexagon, octagon, whatever. That means, like for instance, a stop sign that we come to on the street. A stop sign is a regular octagon, okay? Because all sides of that octagon, all sides of that stop sign are the same length. So it's an equilateral octagon. All sides are marked the same, that means it's equilateral. If all angles are marked the same, that means it's equiangular. If it's both equilateral and equiangular, if it's both of those, then we say that it is a regular polygon. So the 2 most common types of regular polygons would be an equilateral triangle and a square. Okay, a square would be a regular quadrilateral because all 4 sides and all 4 angles are the same. A stop sign would be a regular octagon because all the sides, and I know you probably don't know that, but it is, all the sides and all the angles of that stop sign are the same. So really just knowing what the word regular means and how we're going to use it. Okay, on this one here, we have 4 different pentagons I want to identify the one that is equilateral, but not equal angular. Okay? So first of all, is this one here equilateral? Just off of looks. Does it look like all 5 sides are the same length? No. Okay? This side here definitely doesn't look the same as like BC. Okay? So this is not an equilateral pentagon. So I'm going to cross it out. Okay? And I'll just say not equilateral. Do these 5 sides look equilateral? I know they're not marked, but just off the looks of them, do they all 5 look pretty close to about the same? Probably so, okay? What about this one here? Just look at like DC and AB across from one another. Do those two match up? Are they the same length? Probably not, right? So this one here we would say not equilateral either. Okay? This one here is equilateral, okay? But if I look at the angles on this one, what would I say about it? They also look equal, right? It looks like this figure is perfectly equal all the way around. And so this one would be the regular polygon. Well, we're not looking for the regular polygon. We're looking for the one that has sides the same, but not the angles. These angles here are 90, or look to be 90. This one's obtuse, this one's acute. So these angles are definitely not the same. So the sides look like they're the same, okay? We have 5 sides that look to be the same length. I know they're not marked, but they look pretty close to be the same length. But the angles are definitely not the same. So we would say that this one is equilateral, but not equal angular. So this is the one that we're looking for. Okay, but be really careful of the wording. Okay, the wording is kind of tricky on some of these. So you got to be careful of what it's asking. Okay, on this one here, home plate on a baseball or softball field. Is the polygon regular? Explain your reasoning, okay? So I look at A, B, and D. A, B, and D are what kind of angles? Right angles, okay? Are E and C right angles? No, they look like they're obtuse angles, right? We don't know the actual measure of them, but they don't look to be right, okay? And so is this regular? And we would say no. And not all angles are congruent. So if I wanted to prove it and say, what is the measure of angle C and E? How many degrees would there be in this figure? How many sides does this home plate have? How many sides in that figure? It's 5, right? So if I wanted to figure out how many degrees are inside of that figure, we go back to that formula that we used early on today. 5 sides, so 5 minus 2 times 180 is 540. We have 3 90-degree angles. So I'm going to go 90 plus 90 plus 90. Okay, I don't know E or C, so I'm going to put an X by them. They're unknown, right? So whenever something's unknown, we put an X by it because we're trying to figure it out. So we're going to say plus X equals the total. Those are my 5 angles, right? 3 90-degree angles and 2 that we're trying to find. These 3 are going to add up to be 270. 90 plus 90 plus 90. X plus X makes 2X. Okay, and then we're going to solve for X. So we're going to subtract 270. And then we're going to divide by 2. Okay, and then that kind of proves to us that these angles here are 135 degrees, definitely bigger than 90, so they're definitely not the same. Okay, this one here would be very, very similar. I don't think I'm going to go through that one because I'll write it out for you here, and you can solve it if you want to. But x plus 93 plus 156 plus 85 equals, and it's still a five-sided figure, so it's still going to be 540. The only thing different here is that the three sides, or the three angles, are not the same. So they're just going to add up all together. And then you would work backwards to solve for x. Okay, but S and T are marked the same, so they are the same. So we know that they should be the same angle measure. Okay. One last thing that I'm going to cover real quick, because you're going to see this word today. I don't think you're going to have to identify it, but sometimes polygons are identified as convex versus concave. A convex polygon is kind of the way that we're used to seeing a polygon drawn. That means all the sides are like pointing outward. A concave polygon is where two of the sides kind of cave into the inside of it. Okay, so concave comes in, convex flexes or goes outward. It's not going to the inside.